Okay, welcome back everyone. I hope you're doing well. And it's nice to see all of you in the virtual world again. And I hope you survived this very hot and humid weekend we just had. So take care of yourself and stay hydrated during these warm summer days. Okay, so just so everybody's on the same page, you know that you have your second lecture exam this coming Thursday. Okay, that will be on chapters 6, 7, 8, 9, and 10. Okay, so I sent out a study guide last week on the exam. Do you have any questions about the study guide or about the exam at this time? Okay, everybody's quiet, so I will assume that you're okay with the exam. I will be sending out some information this afternoon with the typical email. And since Thursday is an exam day, we will also start our lecture late to give you a little bit of time to take that exam. So I'll put this in this afternoon's email, but expect that on Thursday, we will start our lecture at around 12:55 p.m. 12:55 for lecture on Thursday. Okay. So also, I indicated in last week's email about the need to finish up the lab portion of the curriculum. And so there are activities in the 6th and 7th lab exercises for you to do. And that was indicated in last week's email. Do you have any questions about what you're being asked to do for lab? Okay, all right. Okay, folks, so let's, believe it or not, we're coming in towards the bottom half of the summer semester for you, right? We only have 2 more weeks after this week. I basically have five lectures with you remaining. And one of those is an abbreviated lecture on Thursday. So we kind of have 4.5 lectures remaining before the very end of our term together. Okay, so I mean, that's a good thing. I know everybody's ready to finish things up, but it's extremely important that you stay focused because there are going to be a lot of things happening here at the end. And so you want to stay organized and stay focused with your study efforts. Before we start some new material here one last time, is there any questions you have about anything for our course that might benefit others to know the answer to? All right, it's great to see you folks. Let's get started. We're going to continue. Okay, so questions popped up on the chat window from Julia. Is the exam worth the same as the last lecture exam? And the answer on that is yes, Julia. That doesn't mean it necessarily has the exact same number of questions, but based on a percentage, it is the same percentage as the previous exam. Okay. Anything else? All right, folks. Let's get back into chapter 10. We were talking about the endocrine system and hormones. Before I move away from our video window here, do you have any questions about chapter 10 content, about the case study we did with insulin, right? We drew that PowerPoint picture of insulin approaching the surface of the cell, binding to the insulin receptor, which then changed the shape of the underlying enzyme to turn it on. The underlying enzyme then activated and manufactured the second messenger, cyclic AMP. Cyclic AMP then went through the cytoplasm of the cell and activated other molecules in a domino-like sequence of events, which led to the opening of the glucose receptor to bring glucose into the cell. That's how you lower blood sugar, by having the glucose actually enter the interior of the cell, either skeletal muscle cells or liver cells. Okay, all of that was an acute response because it happened very rapidly. Then we talked about how if you have a very poor diet and you eat a lot of sugar all the time, that the cells have to adapt. An adaptation means that some of the genes in the nucleus have to be turned on to make additional molecules to provide additional capacity to the cell to lower blood sugar more rapidly. And because that response takes some time and has lasting consequences, that is called a chronic response. So do you have any questions about that? Okay, not seeing anything. All right, so let's go to our Microsoft Word document and continue our note taking from chapter 10. Okay, so the chat window is up. If you need to get a hold of me or if you have questions, please feel free to use that. And the Microsoft Word document is also on the screen, and hopefully you're able to see that without any problem. Okay, so the next small topic in chapter 10 I want to talk about before we start talking about specific examples of hormones, I need to mention to you that hormone secretion, the release of hormones themselves in your body, is under two different types of feedback, either negative feedback or positive feedback. Okay, so let's see. The title here would be Regulation of Hormone Secretion. Okay. There's two forms of regulation, okay, and they are negative feedback and positive feedback. Okay, so in the case of negative feedback, an example of negative feedback is something that seems negative feedback takes place anytime the initial condition or stimulus is actually being reversed. Okay, negative feedback implies that the starting conditions are reversed. Okay, the starting conditions are reversed. For example, okay, so we've been talking, we talked a lot last time about high blood sugar and about how insulin works, and we're going to revisit that a little bit today when we talk about diabetes. But as an example, because you're already familiar with it now, right? We've already been thinking about this, talking about it, putting it in your notes. So Pete, you say that you can't see my screen. It's really blurry. Folks, question coming through the chat window. Can you see my screen clearly? Okay, Julia, Catherine, Alyssa, Paquasha all say yes. Okay, Pete, so I'm not sure, obviously from time to time we do have some technology issues. I would say that if most folks are seeing it clearly, that it might be a problem on your end with your bandwidth or something going on with your internet connection. Okay, so I'll leave it to you to try to wrestle with those sorts of things. Obviously, I know it's a hassle and it's a pain. Do your best. The video is being recorded so that if you need to watch it again, you can watch it. Okay, so I've tried to boost the size of the screen just a little bit. Maybe that's a little bit better for you. Okay, so we're talking about the regulation of hormone secretion. Negative feedback implies that the starting conditions are reversed. As an example, okay, if you have high blood pressure excuse me, if you have high blood sugar, the pancreas is going to respond by releasing insulin into the bloodstream. Okay. Now, you know from our conversation last time that when insulin's dropped into the bloodstream, the cells and tissues of your body respond, particularly the liver cells and the skeletal muscle cells of your body respond by drawing that excess glucose into the bloodstream into themselves, inside the cells, into their cytoplasm. So cells respond by lowering blood sugar, okay? And what that means is if blood sugar lowers, then there is a feedback to the pancreas so that the pancreas stops releasing insulin, okay? Feedback occurs which instructs the pancreas to stop releasing insulin, okay? So in this scenario, what we had was we started with high blood sugar, okay, leading to the release of insulin. And what we finish with is lowered blood sugar, leading to the pancreas stopping its release of insulin. Okay? So that's what we mean by negative feedback. It implies that the starting conditions are reversed, right? The starting condition was high blood sugar leading to the release of insulin. Then we finish with lowered blood sugar leading to the pancreas not releasing insulin, okay? Let me say that a little bit cleaner. All right, okay. Folks, does this make sense how negative feedback, you finish with a state which is sort of the reverse or the opposite of your starting conditions? Does this make sense? Okay, Matt, is everybody else okay? All right, okay, good. Okay, so obviously, if negative feedback implies that the starting conditions are reversed, positive feedback means that the starting conditions are amplified, okay, or enhanced if you prefer that language. Implies that the starting conditions are amplified or enhanced, okay? They're made stronger, okay? Now, most feedback in your body is going to be of a negative variety. I mean, think about it. If you are too hot, you sweat to cool yourself, right? That's negative feedback. You start hot and you finish cooling yourself, right? Most feedback systems in the body are in fact negative. Now, there are, however, some examples of positive feedback. Let me give you a hormonal example here, okay? During childbirth, right? During childbirth, okay, the pituitary gland in a woman's brain releases a hormone called oxytocin, okay? I bet you may have heard of oxytocin before. We're going to be talking about that later in today's discussion. But okay, during childbirth, the pituitary gland in the brain releases oxytocin. This leads to a stimulation of uterine contraction, right? To get the smooth muscle tissue that lines the wall of the uterus to begin contracting to help push the baby out of the body. Okay. The physical act of contracting the smooth muscle tissue provides positive feedback to the pituitary gland to increase its release of oxytocin. The contraction of smooth muscle tissue in the uterus signals the pituitary gland to increase its release of oxytocin, okay, to further stimulate uterine contraction, to further accelerate the process of birthing the child, of getting the child out of the mother's body. Which accelerates the process of childbirth. Okay, so in this scenario, you start with a low amount of oxytocin, which leads to uterine contraction. And that uterine contraction then accentuates the production and release of oxytocin. So we end up with a higher amount of oxytocin to accelerate childbirth. Okay, so we start low and we get higher. We amplify the response, right? We amplify what's happening here. Okay. All right. Folks, do you have any questions about negative feedback or positive feedback? As I said, most of our feedback systems in the body are of a negative variety. Okay. All right. If you don't have questions, then what we'll do is at this time, okay, so we spent a lot of time last class talking about the physiology of hormones and how they elicit acute and chronic responses from a cell. So what I'm going to do now is go over a couple examples of specific hormones, okay? As I said, we're not going to get you to, if you're taking our full anatomy and physiology course, we typically ask students to be familiar with about 80 different hormones, okay? So we're not going to do that to you, but if you're headed towards A&P, get ready because there's a lot you have to know, okay? So we're going to go over a couple examples of hormones that are released from various tissues of the body and just make a couple comments about each one to give you a little bit of feeling for how broad hormonal capacity really is. So let's take a look at page 173. Okay, page 173 in your textbook. Examples of hormones in action. Okay. All right, now I'm not going to go over everything in this page, but there's certain ones that I intentionally want to talk about because they're either interesting or because they illustrate certain principles that I'd like you to start getting familiar with. Okay, so first off, we have the pituitary gland. Okay. Okay. The pituitary gland is highlighted at the very top of page 173, and you can see exactly where it is at sort of the base of your brain. Okay, and you notice it has a rearward facing lobe, which is the posterior lobe, and it has a frontward facing lobe, which is the anterior lobe. And you can see that this tiny little bit of tissue in your brain secretes a whole bunch of different hormones. Okay. You can also see that it's tucked inside a pocket of bone that actually makes up your skull. That little depression there is actually known as the sella turcica, and it's found in the sphenoid bone of your skull. At any rate, let's talk about a couple of these hormones. I don't much care if you know whether it's the anterior or posterior lobe. That doesn't matter too much to me right now. But let me mention a couple of things here. First, we have growth hormone. Okay, growth hormone does exactly what you think. We've talked about growth hormone in limited fashion in another chapter when we talked about the growth of your bones at the cartilaginous growth plates, also known as the epiphyseal plates, right? So growth hormone is released by the pituitary gland, and this hormone stimulates the cells of your bones to do two things. Okay, to increase their numbers, which means to reproduce. Okay, so cells reproduce themselves. All right. Question coming through the chat window. What is the type of cell division taking place when cartilage cells in the bones reproduce? What is the type of cell division taking place when cartilage cells in the bones reproduce? Folks, we have not talked about it in this course, so I'm just curious if you know. I would be willing to bet many of you do know the answer to this question, but you may not be aware that you know. Let me ask you, or let me give you a hint. The answer to my question is a word that begins with the letter M as in Mary. Okay, Emily, very nicely done. Okay, Emily's got it for us. Mitosis, that's right. So in response to the presence of growth hormone, cells in the growth plate will perform mitosis. Okay, so it increases mitosis. So we get more cells. Not only do we get more cells, but each cell that already exists is told to increase its volume. So there is an expansion of the cytoplasm, so that, you know, if a cell were like a balloon, we'd be putting more air into the balloon to inflate the balloon so it looks bigger, okay? To increase the volume of each cell. So our bones grow by taking the cells that are already present and making them larger, and taking those same cells and reproducing and making more cells. And that's how our bones grow, so that we get bigger and sometimes thicker, if you will. Okay. So, of note, okay, you may be interested to note that there actually are a couple conditions that can result from abnormalities in growth hormone levels. Okay, and I think we already kind of all know this. I mean, do you know who I mean by a former wrestler and actor who's now deceased by the name of Andre the Giant? Okay, hopefully you know who I'm talking about. Well, Andre the Giant was a very large man, and he suffered from pituitary giantism. In other words, his body produced too much growth hormone when he was a child, and he became unusually large. Okay, so folks, on page 177 of your textbook, we have figure 10.7, which shows you Robert Wadlow, who's also a pituitary giant. And take note that he grew to a height of 8 feet 11 inches tall. Really quite astounding if you think about it. but also take notice that he died very young at the age of 22. So while it might seem kind of neat in a Ripley's Believe It or Not sort of fashion to grow to be that big, typically folks that grow very large have a shortened lifespan because the body has just not been engineered to grow so large. I mean, the larger you are, the more blood vessels you have, the more blood has to be delivered to more distant locations of the body, the harder it is on your heart. It just stresses your body out to be that physically large. Okay, so if you have too much growth hormone produced during the childhood years, this will lead to giantism. Matt, are you making a statement or asking a question? Okay, thank you so much. I was not, I'm assuming you're talking about Andre the Giant, and I think I did hear that some time ago, so thank you for sharing. Okay. So folks, you can have too much growth hormone, and while that seems kind of neat, it often really is not that neat, okay? You can also have too little growth hormone during the childhood years, and that will lead to a case of pituitary dwarfism, such as you see on page 178 of your textbook, okay? Too little growth hormone produced during the childhood years leads to dwarfism. Okay, there are actually different kinds of dwarfism as well as giantism. So what we're talking about here is pituitary giantism and pituitary dwarfism. Okay, but you can see the outcome of that on page 178, figure 10.9. Now, usually abnormalities in growth hormone levels are most pronounced by unusual production during the childhood years. However, it is possible to have an unusual amount of growth hormone produced during the adult years of your life, such as 18, 19, 20, and onward, that can lead to a condition you see on page 177, figure 10.8, which is acromegaly. Okay, so too much growth hormone produced during the adult years leads to acromegaly. Okay, and with acromegaly, what you will notice there as you scan the images of figure 10.8 is that typically you have facial features and hand features where the bones of the body they really thicken sort of abnormally, okay? So that, by the time that woman reached age 33, she has a very prominent brow, very prominent nose, okay? And that's due to the over thickening of the bones of the face. All right. Okay, so I am not aware, which is not to say it doesn't exist, but I'm not aware of too many consequences of having too little growth hormone during your adult years. Okay, typically we don't think about that too much. For those that are, interested in trivia kind of things, there actually is a black market on the internet for growth hormone. People will sell you growth hormone, at least what they claim is growth hormone, because this idea has gotten out there into the public that growth hormone is sort of a chemical fountain of youth. That if you take growth hormone in your middle age years of your life, that it will help rejuvenate your body and things like this. Folks, there is no scientific basis for this, okay? But it's like anything. People will if you say something enough, some percentage of people are going to believe it. Okay, so just be careful out there. There is no scientific foundation for taking growth hormone in your middle age years. Okay, do you have any questions right now? All right, so growth hormone is something that I think we can all appreciate. We've had some exposure to that with, certain actors and people that are kind of famous that we know something about, such as Andre the Giant. There's some other hormones, though, from the pituitary gland that I also want to highlight for you. One of those is prolactin. Okay, prolactin is the hormone that stimulates mammary tissue to produce milk. Okay, now that is interesting enough in its own right, but I will be contrasting that with something else very soon, which is really the reason I'm talking about this. Okay, but prolactin is released by the pituitary gland, and it is the hormone that stimulates the production of breast milk. So I have a question for you. Okay. In the male body, can males produce milk? What do you say, folks? Can males produce milk? Okay, so Matt says rarely yes. Okay, do you agree with him? Alyssa says yes. How about the rest of you? Queen says if they have a disorder. Well, that's not entirely inaccurate. Okay, the answer is yes, folks. That's right. Males do have all of the biological equipment, all of the glandular tissue needed to actually manufacture milk. Typically, we don't because of differences in our hormone levels, but it is possible for males to manufacture milk. Okay, and we know this from two sources of evidence. First off, anybody that's been around newborn infants knows that it's fairly common for newborn male babies to actually manufacture some milk. And that's because the male baby is still responding to the hormones that are present in the mom's bloodstream. Okay? So male babies often produce milk in response to the mother's prolactin levels in her bloodstream. Okay. Also, you may be aware, for any of you that have studied, some history, that there have been documented cases that came out of Vietnam where we had, primarily men, but occasionally women, but primarily men that were prisoners of war, right? They were captured and they were put under very extreme, stressful conditions. And so it's been documented that some men that were in prisoner of war camps, they were under such stressful conditions that their body's physiology, due to the stress, began to dramatically change in such a way that some men in prolonged periods of captivity actually began to manufacture milk from their mammary tissue. Okay? Male prisoners of war during captivity in Vietnam were documented to produce milk. Okay, so obviously, they were under extremely stressful circumstances, not normal circumstances. But again, it highlights the reality that males do have the necessary anatomical structures needed to manufacture milk. Okay, questions, folks? All right, let's continue here. Let me contrast. Okay, so, whoops, I need to change these a little bit here so the notes make sense. Okay. All right, give you some space here. Okay, so next hormone is oxytocin. Okay. Oxytocin is also released by the pituitary gland. Okay, it's actually manufactured by the hypothalamus in the brain, and you know about the hypothalamus because we studied that in chapter 8, and you're going to be testing on that on Thursday, right? So you know about the hypothalamus. Okay, the oxytocin is manufactured by the hypothalamus, but it is stored for release in the pituitary gland. Okay, so that shows you there's some nuances here to our understanding of things, right? It is fairly common to have one tissue make a hormone and a different tissue control the release of that hormone. So at any rate, oxytocin is made by the hypothalamus, but it's stored for release in the pituitary gland. Okay, as you may be aware of, oxytocin, it's known as the bonding hormone, right? And the idea with the bonding hormone is that doctors and scientists that have been studying these things over the years, they have noticed that, you know, in the minutes, an hour or so after sexual intercourse, after sex between a couple, that typically that couple, both men and women, will experience a boost in their oxytocin levels. And the thinking behind that is that the boost in the oxytocin levels has something to do with emotional bonding between the couple that just engaged in sex, right? So it's called the bonding hormone. Okay, levels increase in people immediately following sex. And in addition to that, might be interested to know that people that have been studying animal science have noted that if you have a dog at the house, often when you feed the animal, that animal will release oxytocin in response to the person that is actively feeding the animal. So if you have, let's say you have 4 people in your family, but mom always feeds the dog, then the dog is going to release extra oxytocin every time mom feeds the dog, and the dog's going to bond with mom. Okay, so the feeding of animals actually leads to releasing oxytocin in the animal body, increasing bonding. Okay. Okay, so oxytocin is called the bonding hormone. Okay, in addition to this, from our discussion about positive feedback that oxytocin is also a hormone that stimulates uterine contraction and helps accelerate the birthing process. Okay. But the third thing that oxytocin actually does, and really the reason I'm putting it into your notes now, immediately after we talked about prolactin, right? We just had prolactin, which stimulates the mammary tissue to produce milk. Okay. The oxytocin stimulates the release of milk from the mammary glands. And so the point I'm trying to illustrate here is that with hormones, okay, quite often you have one hormone stimulating the production of a substance, right? Milk's being produced. Okay, it's being produced. It's not being released. It's being produced by prolactin. It's being stimulated to be manufactured by prolactin. And then oxytocin stimulates the release of that substance. Okay. So let me highlight this in your notes. Note how prolactin stimulates the production of milk, but oxytocin regulates the actual release of milk. Okay? And that's a common theme in the body. And so this is just an example of how that happens. Okay. Do you have any questions, folks? Okay. Another hormone. Okay, letter D here. Another hormone that I'd like to bring out is follicle stimulating hormone. Okay, this is also released by the pituitary. Pituitary does quite a lot, doesn't it? So you can see if you have a pituitary gland disorder, you might really create havoc in the body because hormone levels might be all out of balance. All right, so follicle stimulating hormone, it was named because scientists first discovered it when they were studying reproductive topics in a woman's body. But please understand that both sexes, male and female, produce this hormone, and that's generally true of all our hormones, right? Both sexes produce all the hormones, generally speaking, but in simply different amounts. Okay, so follicle stimulating hormone. Okay, let's put it this way. In women, follicle stimulating hormone promotes the development of egg cells and the secretion of estrogen from the ovaries. Okay, because you know that in women, baby girls are born with all the egg cells they're going to have through their reproductive life, right? And then as they grow up and mature, some of those egg cells begin to mature, okay, and allows a woman to potentially conceive at some point. So in women, follicle stimulating hormone promotes the development of the egg cells and stimulates secretion of the hormone estrogen from the ovaries. Okay, and I'm going to highlight something there in just a moment. Okay, in males, follicle stimulating hormone, obviously it does not promote the development of the egg cells, but follicle stimulating hormone does play a role in maturing the sperm cells in men. Okay, now the reason I'm pointing this specific hormone out is that follicle stimulating hormone is an example of what we call a tropic hormone. Okay, tropic is a vocab word for you on your exam. Tropic hormone. Okay, and this is what it means. A tropic hormone is a hormone that's released by one tissue, secreted into the bloodstream. That hormone travels to a different tissue at a different destination of the body and stimulates a different tissue at a different location in the body to release a second hormone. notice how follicle stimulating hormone, which is released from the pituitary gland, stimulates the secretion of the hormone estrogen from the ovaries. That's a perfect illustration of the idea of a tropic hormone, okay? Note how FSH, okay, so we'll FSH for short here. Okay, note how FSH is released by the pituitary gland in the brain, and it stimulates the ovaries to release estrogen. Okay, so a tropic hormone is a hormone that's released by one location, which then stimulates a second location in the body to respond by releasing a second different hormone. Okay? Folks, do you have any questions right now? Okay. Sounds like everybody's okay, and that's good. So what I'm going to do next is move to the pancreas. Okay, so you can see the pancreas on page 173 down on the right-hand side there, kind of tucked right behind your stomach a little bit. Okay, and so we're going to talk about some hormones that are extremely important in the regulation of your blood sugar. So this ties into our conversation from last time. Okay. Let's see here. This should be number 2. Okay, number 2, the pancreas. Okay. All right. So let's get some basic framework down here, then we can talk about some things. Okay. The pancreas, you can see for yourself from reading your own book there that it releases 2 very significant hormones. It releases insulin and glucagon. Okay. Okay, it releases insulin to lower blood sugar through the mechanism that we highlighted last class on the PowerPoint drawing. Okay, so it releases insulin to lower blood sugar, and it releases glucagon to elevate blood sugar. Okay, so we tend to focus on blood sugar being too high with the disease of diabetes, and so we want to bring that high level down. But you have to admit that there may be times when your blood sugar is actually too low for a variety of reasons and circumstances, and your body needs to be able to recover from that by boosting the blood sugar back up. Okay, so if we have something that can lower it, we need something that can raise it back up. Okay, so this is going to take us into a discussion of some different topics here. So let's start with a question. What is normal fasting blood sugar? What is normal fasting blood sugar? When you get up in the morning after having been asleep for 7 or 8 hours, so let's say you go to bed at midnight, you wake up at 7:30. Before you have breakfast, if you were to take a sample of your blood and measure the blood sugar level, what should it be? What is normal fasting blood sugar? You have any ideas, folks? You see how, if you don't know this, do you see how we all, and I'm guilty of this too, do you see how we all kind of take our health for granted? Because, why should I know it as long as everything's working properly? There's a very good chance statistically that several of us present in our virtual class today are at some moment in life going to develop diabetes. So what should normal fasting blood sugar be? Anybody know? right, so okay, Alyssa, I thank you for your effort. Okay, very nice. Um, Alyssa, Jennifer, Quinn, good. Okay, that's right. Okay, so you will see if you read different textbooks and reference manuals, you might find a slightly different statement of what normal is, because sometimes even the experts don't quite agree on that. Okay, but you know, I think 70 to 120 milligrams is not a bad idea. I would probably tighten that up a little bit. Okay, but I'm not going to argue that you were wrong. I'm going to say normal should be about 80 to 110. And for folks that have been looking at it, what are the units? Because milligrams is not correct. Alyssa, you gave me a unit, but you did not give me a complete unit. 80 to 110 what? Right, it's like saying I have 70. Well, 70 what? 70 apples, 70 pairs of shoes, 70 televisions. Jennifer, milligrams. Jennifer, milligrams is only half the answer. Milligrams is only half the answer. Can anybody help us out here? Ah, there we go. Okay, beautiful. All right, milligrams per deciliter. Okay, so that's exactly right. And what that means is, okay, what that means is your normal fasting blood sugar in every tenth of 1 liter of your blood plasma, you should have 80 to 110 milligrams of sugar. Okay, that's what that means. Normal fasting blood sugar of 80 to 110 milligrams per deciliter means in every 1/10 of a liter, in every 1/10 of a liter, you should have 80 to 110 milligrams of sugar dissolved in that blood plasma. That's what normal fasting blood sugar is. Okay. All right. So I won't ask you if you know what a deciliter is or milligrams, but suffice it to say, right, as we get into more practical applications, we have to have an understanding of what units really mean. Okay. All right. So, okay. So, another question. Okay. If blood sugar is too high, we know that insulin will stimulate the tissues to absorb the sugar inside each cell. What do the cells do with it? Okay, if blood sugar is too high, we know that insulin will stimulate the tissues to absorb the sugar inside each cell. What do the cells do with it, folks? Okay, now you know, hopefully, that insulin will stimulate a lowering of the blood plasma sugar level because cells will take that excess sugar inside the cytoplasm. Well, once they have that excess sugar, what do the cells do with it? There's more than one answer here, folks. More than one answer. Okay, Matt, I like that one. That's a good one. Okay. So let's write Matt's down, and then Quinn will get to your statement. Okay. So cells may use the glucose to make ATP to power processes like muscle contraction. Okay. All right. Now, Quinn, you say in your answer, they will send it to places like muscle cells. So I'm a little worried about how you answered that when you say they. Who is they? I think you mean cells. So you're saying cells will send sugar to muscle cells. Well, no, that doesn't make any sense. Okay. So cells are not going to send it to other cells. Whatever cell takes it in is going to use it. Okay, but it's not going to transport it. One cell is not going to transport it to another cell. Okay. So that's a big important one. Yes, the cell may use the glucose to make ATP to power processes like muscle contraction, or if you're a neuron, to power an action potential, or even the maintenance of normal resting membrane potential, moving the sodium and potassium ions, as we talked about a little bit in chapter 7, that requires the use of ATP. So as you sit here trying to make your mind as absolutely blank as you can, create a blank state in your mind, you're still using ATP. You can't avoid it. Okay? Is there anything else that cells might do with it? Okay. Can you imagine a scenario where a cell takes in so much extra sugar that the cell cannot immediately use it to make ATP? Okay, Alyssa, very good. That's right. So if a cell has too much glucose that it can't even burn it immediately to make ATP, it will store it. So Alyssa, do you know in what form it will store it as? Okay, not fat, Matt. That no. Okay, all right. So people want to say fat. Okay, here's the deal, folks. If your body is functioning in a normal, healthy state, and there's no disease processes taking place, generally speaking, that excess glucose will not be stored as fat. Okay. If, however, you have some disease processes occurring, it is possible that the glucose can be biochemically converted into fat. That is true, okay? But generally speaking, it's not going to start that way. Okay, so here's my question, okay? What is the natural, coming through the chat window, what is the natural, normal, polymerized version of glucose in animal tissue called? What is the natural, normal, polymerized, meaning the glucose is linked together in a chain? What is it called? Let me give you a hint. The answer to my question is a word that also starts with the letter G, as in good. Emily, you got it. Very nicely done. Glycogen. That's right. Okay, so excess glucose that is even too much for the cell to use immediately as a fuel source to make ATP, that excess glucose is going to be biochemically linked together into a repeating chain of glucose molecules. That's what I mean by polymerized. So a glucose molecule is going to be linked to another glucose molecule, it's going to be linked to another glucose molecule in a chain of glucose that is called glycogen. Okay, so excess glucose will be linked into a chain of glucose called glycogen. Okay. So folks, be very careful here, because in this topic that we're talking about, we have three words that start with the letter G, and they kind of sound the same, and it's very easy to accidentally swap one for the other. I'm going to highlight these three G words by underlining them in your notes. Notice we have glucagon. Glucagon is a hormone. We have glucose, which is a monosaccharide. And we have glycogen, which is a polysaccharide. Okay, so be very careful that you do not confuse these three words that start with the letter G. Okay. Now there's another possibility of something a cell might use the excess glucose for. Does anybody have another possibility they want to contemplate? Okay, well, not to drag this out too long, because if you don't get it immediately, my suspicion is you probably won't get it. And that is, you appreciate that glucose and carbohydrates in general can actually be used to build structures, physical, three-dimensional structures that are important to the behavior of a cell. And the structures that I'm immediately thinking about are some of the carbohydrates that you see hanging on the outer surface of the plasma membrane of a cell. Take a look. If you have your textbook, I hope you have it available. Keep your place in chapter 10 that we're talking about on page 173, but then go back to page 47. Go back to page 47 and take a look at figure 3.6. And do you notice there that on figure 3.6, you have these things called glycoproteins and glycolipids, okay? And basically what they are proteins that have carbohydrates like glucose attached to them, or lipid molecules that have carbohydrates like glucose attached to them, and they act as receptors for other molecules in the body to attach to provide information for different kinds of processes, such as defining your blood type, whether you're blood type A, blood type B, blood type AB, that sort of thing. So the bigger point I'm trying to make is excess glucose is sometimes used to build other types of molecules that have structural properties and biochemical properties that will be useful for the cell and for the body to use as sort of information to help the body function correctly. Excess glucose can be used to build three-dimensional structures that have biophysical functions in the body and physiological functions in the body, such as defining blood type. Okay? All right. Gang, any questions so far? Okay. In a very silly way, maybe as a kid, you took some gingerbread and made a gingerbread man out of it, or you took some graham crackers and made a graham cracker house of it, or you took some macaronis and built something out of macaronis. In other words, the cells can take their molecules and do other things with it. build other structures with it that have function and value to the cell. All right, any questions? Okay. All right, folks. So if there's no questions so far, let's start talking about this dreaded disease that we call diabetes. Okay. All right. So I am pretty much finished on giving you notes about hormones. I mean, we could go on for the rest of our time and not get to the end of the hormones, so I don't want to do that. I'd rather talk to you about something that intersects with our everyday lives as people living, you know, in a community here. We all, I mean, let me ask a question through the chat window. Do you know anyone that struggles with diabetes? Please type yes or no into that window. Okay. Okay. All right. So suffice it to say, diabetes is pretty common. Alyssa, you really don't know anybody that has diabetes? I'm a little shocked by that. Okay. All right. But you can see most of us, in fact, do have diabetes. It's pretty serious. Okay. So it's a very common situation. Now, okay. So we're going to talk about diabetes, and diabetes itself is a very complicated disease. If it wasn't complicated, we'd probably already have a cure for it, but we don't. Okay. So diabetes. Okay. When you say diabetes, you are referring to the phrase diabetes is a sort of a catch-all phrase. The common characteristic of all diabetics is an elevated blood sugar level. Okay, so diabetes as a term refers to a group of metabolic disorders. Diabetes as a term refers to a group of metabolic disorders that are all characterized by an abnormally high blood sugar level. Okay, so this is somewhat separate from our previous notes here. Okay, so there's actually different types, there's different forms of diabetes. And if I'm being quite frank, even today in 2020, we're starting to realize that things are even more complicated than we previously thought. But I'll get to that in just a moment. Okay, so the two major groups of diabetes are diabetes mellitus and diabetes insipidus. Okay, now I'm going to spend most of my time talking to you about diabetes mellitus because diabetes mellitus by far is the most common form of diabetes that impacts the greatest number of people on planet Earth here. Okay, that's not to say that diabetes insipidus is not serious. It is, but it doesn't impact as many people. Okay, so what I'll do is give you a quick characterization of diabetes insipidus, and then we'll come back and spend our time talking about diabetes mellitus. Okay, so diabetes insipidus is also characterized by abnormally high blood sugar level, and a patient that has diabetes insipidus, this form of the disease occurs when the kidneys are unable to conserve water. Okay, they're unable to conserve water, so the blood volume actually drops, which actually elevates the sugar in the remaining volume of blood that's present. Okay, so and let me type that out. We'll say it again to make sure it's getting through to you. Diabetes insipidus occurs when the kidneys are unable to conserve water, meaning more blood plasma is removed from the body as urine than is supposed to be. Okay. Let's see, I typed that note wrong. Occurs when the kidneys are unable to conserve water, meaning more blood plasma is removed from the body as urine than it is supposed to be. Okay. This has the unintended consequence of concentrating the sugar in the blood plasma remaining. Okay. So, okay. Let's see. So just to be sure we're okay here, let me ask you a question. Okay. And it's related to this idea of what's happening in folks that struggle with diabetes insipidus. Okay, so in a person with diabetes insipidus, their kidneys are creating a larger volume of urine than should really be happening. And when you create more urine, the place you get the liquid for the urine is the bloodstream, the blood plasma. So to produce the urine, you lower the blood volume. By lowering the blood volume, you concentrate the sugar that's present in that blood. Okay, so here's a question for you. If you had a cup of coffee and if you had a cup of coffee with 1 teaspoon of sugar dissolved in it, how could you make the coffee sweeter without putting more sugar into it? Okay, folks, what do you think? If you had a cup of coffee with 1 teaspoon of sugar dissolved in it, how could you make the coffee sweeter without putting more sugar into it? Okay, thank you, Jennifer. And that's why I'm glad I asked these questions, and I appreciate your responses. Okay. No, I'm not. You folks sometimes make me laugh. Okay. Folks, I'm not suggesting that we add anything extra to this cup of coffee. You know, I know there's stevia and I know there's sugar substitutes, you know, sweet and low and all that kind of good stuff. I'm not suggesting that you add anything else to it. Okay. The answer to my question is all about, do you understand the description of diabetes insipidus? If you had a cup of coffee with 1 teaspoon of sugar dissolved in it, how could you make the coffee sweeter without putting more sugar into it? And I sincerely do appreciate all your answers and participating, but that's not what I'm getting at. Okay. Anybody? So I'm a little concerned that I'm not getting the answer I need, which makes me wonder if I've done a poor job describing diabetes insipidus to you. Okay, folks, let me ask you this through the chat window. Through the chat window, for this coffee to taste sweeter, does the concentration of the sugar in the coffee have to increase? For this coffee to taste sweeter, does the concentration of the sugar in the coffee have to increase? Okay, Quinn. Quinn, you say if you take out coffee, you are left with more sugar. I like that a lot. So how are you going to take the coffee out? You know, I mean, if coffee is basically water, how are we going to remove the water? Okay, Quinn, evaporate it. So how could we accelerate evaporation of the coffee? All right, Alyssa, boil it. In other words, heat it up, right? If we heat our cup of coffee enough so that some of the liquid water of the coffee starts to evaporate, aren't we going to reduce the volume of water that sugar is present in? Which means the concentration of the sugar is going to go up. Okay. If we heat the coffee so that some of the coffee, meaning the water, evaporates, then the sugar will be dissolved in a smaller volume, which increases the concentration of the sugar. This will make the coffee taste sweeter. Okay, let me read that again. Think about it, folks. If we heat the coffee so that some of the coffee, the water of the coffee, evaporates, then the sugar that's present in the coffee will be dissolved in a smaller volume of liquid, which increases the concentration of the sugar. This will make the coffee taste sweeter. Folks, does this make sense to you? Okay, awesome. That's what we're here for, folks. Great, fantastic. Okay, does anybody have a question about this? Because what we've just described with a cup of coffee is actually kind of what's happening with your bloodstream. For a patient with diabetes insipidus, their bloodstream is this cup of coffee, and they're not evaporating their blood, but they're removing their blood during a process of forming urine. And so the sugar stays behind in the lowered volume of blood, which increases the concentration of the sugar in that blood. And that's the problem. Okay. All right. Do you have any questions about that? Okay. Sounds like you're all right. So let's now talk about diabetes mellitus. Okay, so diabetes mellitus is the more common, is the more prevalent form of diabetes that we struggle with in society. Okay. Okay, for diabetes mellitus, there's actually two forms of it. And again, I mean, the thing about gaining some knowledge on a topic and becoming educated, as you all are doing at this moment, is that you appreciate that you get to know what you don't know. You get to appreciate that there's a whole bunch of stuff out there that we truly don't understand yet. So diabetes mellitus, it's typically described as two forms of it that exist. But current research is probably breaking down that dogma, two forms exist. Okay, those forms are type 1 diabetes mellitus. Okay, type 1 DM, diabetes mellitus. Okay, and then okay. Folks, it sounds like we might have a little bit of background. If you'd please check your microphones to keep them muted at this time. Type 1 diabetes mellitus. Okay, so question to you. What can you tell me about type 1 diabetes mellitus? Okay, anything you know about type 1 diabetes mellitus, go ahead. Feel free to talk or type it into the chat window. Okay, Pete, you say it can be cured. I'm not aware of any technology that can really practically do that yet. Certainly there are efforts out there to do that, but I'm not aware of common cures at this point. Matt, you say you're born with it. That is frequently true, Matt, but it's not always true. It can be reversed. Well, Jennifer, what do you mean by reversed? Does that mean it can be cured so you don't have to live with it? And then you say, no, sorry, type 2 can. And Quinn, you get many ads about medicine that can help. Okay, that's right. Thank you, pharmaceutical industry, very much. Okay. All right. So let's break this down a little bit. Okay, Catherine. Catherine, how is it managed? Through insulin shots or pills. Okay, very good. Thank you. All right, so good. All right, so everybody contributed. Thank you so much. Insulin injections or pump are very frequently used. Diet is also very helpful, Jennifer. That's right. Okay. Okay. Fantastic. Feel free to continue typing in anything you want to contribute. You all said some very reasonable things. There's nothing that was said that is just absolutely completely false. Let's weed this out in our notes a little bit. Okay. Type 1 diabetes mellitus is often referred to as juvenile diabetes. Okay. And that's because you are often born with it, as Matt indicated, I believe, or you develop it in the early years of your life. That is often true. It's not universally 100% true. Okay. You can be a 43-year-old and develop type 1 diabetes mellitus. That can occur. Okay. So it's often referred to as juvenile diabetes because children are frequently born with it or develop it during childhood, during the first 5 years of their life. Okay. All right. Many of you said that this would be managed with insulin. Okay, that is absolutely true. Okay, a type 1 diabetic patient is going to be insulin dependent. Now, there might be some medications that help a little bit with various aspects of this disease, but generally speaking, if you are a type 1 patient, you are going to require insulin. Okay, patients are insulin dependent. Okay, patients require insulin. Other medications are rarely enough. If you found a medication that was able to manage the type 1 diabetes mellitus without insulin, I would put forth the argument that that's telling us that there are different versions of type 1 diabetes mellitus. And there very well might, in fact, be different versions of type 1 diabetes mellitus. Okay. And as I'm suggesting, research is continuing to uncover these things. Okay. All right. Folks, what's the cause? What is the cause of this disease in children? What is the cause? Okay, Matt, you say a lack of insulin production in the pancreas. That takes us a long way. Okay. Pete, you say bad diets and genetics. Okay. Well, a bad diet's always bad for everything. So you're right, Pete. However, genetics seems to play a major role in this disease. Okay, particularly if you're born with it. That's an indication that genetics is playing a really huge role. Okay, so patients fail to manufacture insulin in the pancreas. Okay, so big question here. Why? Why are patients' bodies, why is their pancreas not manufacturing insulin? So Quinn, you say maybe it is damaged. I'm going to keep picking on you. What does it refer to? Does it refer to the insulin or the pancreas? Okay. Alyssa, you say damage to the pancreas. Okay. And Quinn, you're saying the pancreas. Okay. So what is damaging the pancreas? What's damaging the pancreas? A genetic defect. That's not impossible, Matt, but that's not what we currently think is occurring. Well, it depends on your perspective. Quinn, maybe a tumor. That's not impossible, but it's frequently more common in people and in animals to actually have tumors that overproduce insulin, leading to an unintended low blood sugar consequence. So that's not too common, but I won't say that never happens. I mean, we have to be open to the possibility that biology is broad and all kinds of weird things can happen. That's true, right? It really is Ripley's Believe It or Not. Folks, let me give you a hint and then see if you can take it from there. Does type 1 diabetes mellitus have anything at all to do with your immune system? Okay. All right, what am I suggesting here, folks? Think about the biological weapons story and multiple sclerosis. What am I suggesting? Okay, very nice, Matt. An immune response to insulin. That's exactly the current leading theory on this, okay? The idea is that for reasons that are not completely understood, it appears to be the case that patients with type 1 diabetes mellitus, their immune system has gotten confused and identified insulin as some sort of danger or threat to the body. And in such case, the immune system attacks the cells in the islets of Langerhans of the pancreas responsible for making the insulin. The immune system attacks those cells, kills those cells so that they cannot make the insulin anymore, and all of a sudden the body doesn't make any insulin, okay? weird stuff. But that's what seems to be the case. Okay. A patient's immune system gets confused about insulin, considers it a threat, and destroys the cells in the pancreas responsible for manufacturing insulin. Okay, so in other words, as far as we can tell, type 1 diabetes mellitus is an autoimmune disease. And if I were a betting person, or let me put it this way, if I was a person that had enough money to actually bet, I would bet that many of the diseases that plague us actually have an immune system component to it that we do not fully appreciate and understand. Okay, but at any rate, this is what we believe is happening. So another question comes about. Why in the world should some people have an immune system that thinks that insulin is dangerous? Why the heck is that happening? Okay, well, okay, folks, do you remember in the bioweapon story that I shared with you where the scientists generated this weapon where they took a foreign version of myelin sheath and put it into a bacterium, and then you put this Frankenstein bacterium into the guinea pig's body, and the guinea pig's immune system got alarmed about this foreign myelin sheath, and because the foreign myelin sheath was so similar to its own natural myelin sheath, the immune system attacked both and did damage to the guinea pig's myelin sheath, ultimately leading to death of the animal. Do you remember that? Well, some research has come out probably about 6 to 8 years ago now, so it's still pretty new stuff, where scientists have identified a marine virus, M-A-R-I-N-E, a virus from our oceans, a marine virus that produces a protein that is very similar to insulin. Okay, similar enough that it might confuse the immune system as being something dangerous so that it might attack the own cells of the body that make insulin and destroy it. You say, well, that's great. It's a virus that's been discovered in the oceans. What's that have to do with us? But you recall that a good portion of humanity actually eats seafood. So the idea here is, one possibility is that in our food supply, we are potentially being exposed to viruses that make insulin-like molecules. And in some people, they get exposed to enough of this that their own immune system becomes agitated by it, and then leads to a runaway response where you actually damage the pancreas so it doesn't make any insulin at all. Okay. This is something that's come out. It's definitely come out within the past 10 years. It's not even a decade old. Okay. It has been observed that some marine viruses that we, meaning humanity, are exposed to when we eat seafood produce insulin-like molecules that could be seen as a threat by your immune system. Okay, so you might ask yourself, well, why doesn't every person that gets exposed to this develop type 1 diabetes mellitus? Well, the answer is complicated, and basically we don't know. But think about it. Think about how many people right now are being exposed to coronavirus, and yet only a relatively small percentage of them have serious symptoms. The other folks may not have any symptoms, right? So in other words, we can all be exposed to the same thing, but because we have a different genetic makeup, which defines a different biochemistry in our body, which controls the immune response, that's what's really going to predict whether you're going to develop type 1 diabetes. Okay. So
I do have a question before we continue.
Go ahead.
So you're saying with this whole the virus thing, and I understand that maybe for later on in life, but for those that are born with it, isn't it tied more into genetics and that immunoresponse to the pancreas? So they've discovered how the pancreas gets damaged, no longer produces insulin, but what part of the genetics would cause that immunoresponse in a young kid? And the reason I'm asking is my cousin has type 1 diabetes, and they found out, when she was very little, so she wasn't even at solid foods yet.
Right. That's a good question, Matt, an extremely relevant and reasonable question. I can't give you a satisfying answer, and I don't think anybody will be able to. But what I would say is in the case of, a child that's born with it, there's a couple things to think of. Certainly a child that's born with type 1 diabetes mellitus, you say, well, that child was not exposed to this virus. The child may have been exposed to the virus if the mother had seafood during the pregnancy. That's a possibility. The second thing is, what is it about a person's unique genetic makeup that predisposes them to this sort of inappropriate immune response? That's the piece of the puzzle that humanity, we don't really deeply understand this. And it's going to be a long time before we do.
Gotcha. So this new study is pretty much saying that virus, if that happens to be the case, can actually be transmitted, in utero, kind of like HIV and stuff.
Absolutely. And I will say that for a very long time, I'm dating myself here, but if you went back 60 years, okay, which I'm not 60, but if you went back that far, you would find that the medical community and the scientific community basically had the assumption that the in utero environment was a very sterile environment, that it did not allow for the presence of microorganisms to pass from the mother's bloodstream into the baby's body fluids. We now know, particularly with virus, that is completely wrong. There is a treasure trove, good or bad, for better or worse, of viruses that an unborn child is in fact exposed to during their 9 months of development.
All right. I understand. Yeah, I was missing the tie-in for that virus to juvenile diabetes. Now I see where it's coming from.
Absolutely. Okay. Yeah. Keep asking the questions. That's a good one. Okay. And obviously with many things, the final story on this is unwritten. We just don't have enough information to say so at this point. But the progress of science is slow, right? Think about it. Humanity has been trying to develop an HIV vaccine for at least 40 years, and we still don't have one. And it's not because we haven't been trying, it's just because the damn thing is really, really hard to do. So, it's not satisfying when you have to personally suffer with this situation, but, we are doing the best we can. So, anyway, other questions? Okay, so that's type 1 diabetes mellitus, folks. Okay, and as we've said, these patients are going to be insulin dependent. That means, the child's going to have to receive insulin injections or potentially have an insulin pump surgically inserted so that the electronics of the pump can give the insulin when necessary. obviously not a pleasant thing for anybody, but it's particularly not a pleasant thing, to tell your child that they need an injection every day. That's just not a fun thing to do. Okay, let's go to type 2 diabetes mellitus. All right. Type 2 diabetes mellitus. What can you tell me about it, folks? Tell me everything you know about type 2 DM. Go ahead and type into the chat window or feel free to speak up. What do you know about type 2 diabetes mellitus? Pete, it's more serious than type 1. Well, okay, I think we could argue that point. If for no other reason than type 1 often starts in early childhood, whereas type 2 may not develop until you're 60, so that's somewhat arguable about it's more serious. Jennifer, it can be reversed with diet and exercise. That is sometimes true, Jennifer, but not always true. Okay. Anything else? Okay. Go ahead and comment as you see fit. If you think of something, go ahead. Folks, type 2 diabetes mellitus. Okay, let's wash this. Let's characterize this out in your notes. Okay. Type 2 diabetes mellitus is often referred to as age onset diabetes. And what that means is that the older you live, the older that we all live, the more likely we are to develop this disease. Okay. So my question for you, you know me, I'm always going to ask you, why? Why is it that the older we get, the more likely we're going to develop type 2 diabetes mellitus? Why is that true? I mean, let's think about this for a moment. The older we live, the more likely we're going to develop type 2 diabetes mellitus. The older we live, the more likely we're going to have cancer. The older we live, the more likely we're going to have a stroke. Okay, Matt, you say insulin production slowing down or stopping due to overwork of the pancreas. I will give you that, Matt, that sometimes the pancreas does get overworked during this disease. And when that happens, you will slow insulin production or potentially even stop it. And that's something we're going to talk about here. But that's good stuff. But usually early in the type 2 diabetes mellitus disease, usually the insulin production is overabundant, okay? So Matt, you say it's usually in the case of bad diet. Well, that certainly doesn't help us, right? A bad diet is abusive to your cells and tissues and organs. That is absolutely true. Quinn, you state that our bodies, including our pancreas, get slowed and are slowly dying, which makes it harder to make insulin. There's some good truth to that. There's some good truth to that. I like what you're saying, and I think you're onto something there. I think you're in the ballpark of what I'm fishing for. Okay, folks, let me ask you this through the chat window. Okay, if you had to photocopy a page out of your textbook, and then you had to photocopy the photocopy, and then the photocopy of the photocopy of the photocopy. In other words, if you had to keep taking photocopies from previous photocopies, what would the quality of the 100th photocopy be like? That's a lot of words there. If you had to take a copy of a page out of your book, and then you copied the copy of the page, and then you copied the copy of the page, and then the copy of the copy of the copy of the page, and you keep doing this, what's going to be the integrity or quality of that last photocopy? Isn't it going to be lighter and grainier? And generally speaking, it's going to have lower quality. It might even be unreadable. Absolutely, Alyssa. Okay. All right, so I think we can all agree that the 100th photocopy from all the previous photocopies is going to be of a very poor quality. Now think about this. Your body is made of cells, and while some of them have been alive since you were born, many of those cells have been replaced by copying previous generations of cells. So I tell you again, what's happening to your body when you have cells that when you're age 60 came from photocopying a previous cell, which itself was photocopied from a previous cell at an earlier age. What do you think is going to be the quality of that cell? Okay, it's going to be bad. That's right, folks. This is what I mean by age onset diseases. Age onset, okay? Think about this. Think about age onset. This means the integrity of the cells in your body gets worse the longer you live and the more frequently those cells have had to reproduce and copy themselves. Okay? Think about photocopying the photocopy. All right? So, this is essentially what's going on with type 2 diabetes mellitus. The cells of your body are breaking down a little bit. The integrity of the cells is not as good as they were 10 generations ago because the cells are being reproduced from a copy of a copy of a copy of a copy. Or at the very least, the molecules in a cell are being reproduced from a copy of a copy of a copy of the DNA. Okay? So that's absolutely right. And that's what we think is happening with type 2 diabetes mellitus. Okay? So with type 2 diabetes mellitus, what seems to be the case, at least in patients that this has been studied in the research lab, is that people with type 2 diabetes mellitus typically have cells where there's not a problem necessarily with the pancreas. The problem is within the target organ of the insulin. Okay, so what did we say from last class? What kind of cells typically respond to the insulin? What kind of cells typically respond to insulin? Okay, muscle cells and liver cells. Okay, muscle cells and liver cells. You know, there are other things. I mean, strangely enough, insulin is not only made from the pancreas in your body, but strangely enough, your brain tissue also manufactures insulin. That's something that we're just trying to wrap our brain around at this time scientifically. But at any rate, what we currently believe is the majority of cases with type 2 diabetes patients is that the cells, the cause of type 2 diabetes mellitus seems to be cells that are not able to respond to the insulin anymore. Meaning these patients are insulin resistant. They're insulin resistant. So from our conversation last time and what you've been thinking about, what could make a cell resistant to the insulin? What could make a cell unresponsive to the insulin? What could make a cell unresponsive to insulin? There's one key idea that I'm fishing for, folks. What could make a cell unresponsive to insulin? Now go back to your notes with the PowerPoint drawing when we sketch things out with insulin. What would make that cell unresponsive to the insulin? Okay, Matt, you've hit upon something there that's definitely been documented by medical science. It's a problem with the receptors, either not having the receptors or having mutated or malfunctioning receptors. When you say damage to the cell membrane or lack of an enzyme, that's also a possibility, which is why research is beginning to suggest that type 2 diabetes might in fact have many different causes that are beyond what we currently think is the case. I suspect that is true. So I like how you're thinking. We just can't say definitively whether your idea is correct, Quinn. But we can say that Matt's idea is correct because we have evidence for this. Okay? If a cell had no insulin receptors or had mutated insulin receptors, it would not respond. Okay? And so right now, the current thinking among most of the medical community is that this is really the cause of type 2 diabetes mellitus, is that it is a receptor disorder. It's not a problem with the pancreas. It's not a problem with the insulin. It's a problem with the cells that should be binding the insulin. There's something wrong with the binding event of the insulin to the receptor. And what's been cataloged is that the insulin receptors are often mutated or missing in people that have type 2 diabetes mellitus. Okay? All right. So, another question to you. Okay. What would be the consequence of having cells of the body that should respond to insulin not respond to insulin? What would be the consequence? What would happen? Okay, Quinn. All right, blood sugar levels are going to stay high. That's exactly what I'm fishing for. Okay, blood sugar levels will stay elevated. They will stay high. Okay. So, okay, follow the train of thought here, folks. If the blood sugar level stays high because the cells of the body that should respond to insulin are not responding to insulin, if the blood sugar level stays high, then what organ is going to respond by continuing to push out even more insulin? Let me say that again. If blood sugar stays high, what organ is going to respond to that consistent blood sugar elevation by trying to release even more insulin? Okay, Quinn, very good. The pancreas. If blood sugar remains high, what organ will continue to push more insulin into the bloodstream? Well, the pancreas, right? Here's where I'm leading, folks. If you have a type 2 diabetic patient that is untreated, if you have somebody with untreated type 2 diabetes mellitus, they're not under the care of a medical doctor and they're not doing anything to therapeutically manage their disease, what happens is the blood sugar level stays high because the body is not responding to the insulin that's being released. Since the blood sugar is staying high, that provides positive feedback for the pancreas to produce and release even more insulin into the bloodstream. So all of a sudden you have a situation where the patient becomes hyperinsulemic, meaning they have more insulin in the bloodstream than they should have, because the pancreas sees the elevated blood sugar is not getting lower, so it produces even more insulin and pushes even more insulin into the bloodstream. Okay. In untreated type 2 diabetes mellitus persons, their pancreas will shout extra insulin into the bloodstream, making the person hyperinsulemic. And this is where I can come back around to one of your comments, Matt, and that let me ask this through the chat window, okay? What happens to your car engine if you run it constantly and never give it an oil change? What happens to your car engine if you run it constantly and never give it an oil change? I mean, I have in my youth dated some gals that never changed their oil, and it created some engine problems, right? Okay, it's not going to be a good outcome. Okay, that's the point, that you're going to burn the engine up. Okay, so this is what's going to happen to the pancreas, folks. If the diabetes is uncontrolled, there's no medical care for the patient, the insulin level goes up because the pancreas is constantly responding to the condition of elevated blood sugar. In such a case, you start to overwork the pancreas so much that the pancreas may ultimately collapse and give out and stop producing insulin at all. Okay, let me continue my notes here. In untreated type 2 diabetic persons, their pancreas, okay, wrong there, their pancreas will shout extra insulin to the bloodstream, making the person hyperinsulemic. This can exhaust the pancreas so that it stops functioning and stops making insulin. Okay, now, if this happens, gang, if you have a type 2 diabetic person that's untreated and their pancreas wears out, I mean, this is likely to take a couple years, to be honest with you. It's not going to wear out in a month, right? Your body's very robust. But if you did not take care of yourself for a long time and the pancreas was overworking itself for quite a few years, it is possible that it can give out. If it gives out and stops producing insulin, what kind of diabetes do you have? There it is, Matt. That's exactly what I'm trying to say. It is possible. It is possible for a type 2 diabetic, particularly those that are untreated, to actually convert to the clinical definition of type 1 diabetes because they burn their pancreas out. Okay, now typically this doesn't happen in there, this does not happen if you have access to medical care, which hopefully you should, but we know how politics are. Okay, okay. So my question, which you've answered, and I'll put into your notes, what type of diabetes will a patient have if they stop making insulin? Well, type 1. A type 2 can convert to type 1. A type 2 can convert to a type 1. Okay? So usually the next question that comes out, and it's reasonable, is, well, can a type 1 convert to a type 2? A type 1 can take on the characteristics of type 2, but they're still going to be type 1. If you're not making insulin, you're type 1. But a person who's type 1 and getting up there in their age can also have mutated receptors, so they can take on a combination of type 1 and type 2 characteristics. You can start to see why it is so very difficult to treat all these diseases, because there can truly be a variety of molecular defects that kind of create the same outcome. Okay? All right, questions right now? All right, so we did not talk about treatment of type 2, okay? For type 1, the treatment's obvious, okay? Patients are insulin dependent, they need insulin, okay? Treatment for type 2. Let's see here. I think this is letter C. As some of you have indicated, treatment is variable, okay? At the early stages of type 1 diabetes mellitus, it's very likely that your doctor will talk to you about lifestyle modifications. In other words, if you're early into the disease, or if you're in a condition where your doctor is afraid that you're kind of progressing into the disease, your doctor's probably going to talk to you about your diet and lifestyle choices, right? Are you eating a balanced nutrition, a balanced nutritional diet every day? Are you overeating? What exactly are you putting into your body? Because if you stop some of the bad dietary habits and you get a little bit more exercise, you can often push back the onset of type 2 diabetes. So changes in diet and exercise can help push off type 2 diabetes mellitus. That's true, okay? If the changes in the diet are not enough to completely push back the type 2 diabetes mellitus, and they may not be for a variety of reasons, because let's be honest, a change in your diet is not really going to do much if the DNA of your cells is coding for a mutated insulin receptor. The diet's not going to be capable of fixing that kind of problem. Okay, so other things that could be had are non-insulin medications, and there's a variety of pharmaceutical options out there. You may know some that I'm not aware of. That's very possible. But a well-known medication that's been out there and it's been used for decades is called metformin. Okay, metformin is an insulin sensitizing agent. And that's a fancy way of saying it's a medication that helps the cells of your body bind and respond to the insulin better than they could without the medication. Okay, so this helps cells respond to the insulin. Okay, there are new medications that you've probably seen advertised out there. I think Januvia might be one of them, where the medication is designed to modify your kidney function so that you actually release some of the excess glucose in your urine, so you kind of pee it out of the body. Okay, that's another medication that helps lower blood sugar. Okay, so this modifies urine production to release excess sugar in the urine you produce. Okay, and then, you know, if those medications for a variety of reasons are not successful, or they are not accessible to you, let's be honest, some medications, you know, Januvia is going to be a lot more expensive than metformin because it's a newer drug, and so the drug companies want to recoup their profit. They want to recoup their expenses in developing the drug and make some profit on it, you know, and that's a whole nother conversation. But if you don't have access to the medications, then they're not going to help you. And suffice it to say that insulin is actually fairly lowly priced because it's been around for so long. It's been made for so long. We have efficient ways of manufacturing it today in the modern lab using some genetic engineering techniques that actually sometimes it's cheaper to be on the insulin than it is to be on some of these other medications. But suffice it to say, your disease may progress. It may progress enough that you also have to be on insulin. Okay, and people that are very resistant to insulin, they might need to have very, very high doses of insulin to get their body to respond to it. I know a gentleman who is stick thin. He's very thin. He's not overweight at all. He does not have an ounce of fat on him, but he has type 2 diabetes mellitus, presumably because there's, you know, a problem with his cells' insulin receptors. And every day he has to inject 400 units of insulin, which is a boatload of insulin, simply to keep his blood sugar levels in check. Okay, so use insulin. The more resistant your cells, the higher the medication dose must be. Okay. All right. Questions so far? I know we're getting a little short on our time here, and we're going to be wrapping this up momentarily. Okay. Let me stop the note taking and just talk to you face to face through the video. Okay. All right. So diabetes is a complicated disease. You can see that from the notes we've taken. And it's a very serious disease. Okay, I would encourage you to do everything you can with your personal lifestyle choices to avoid it. Because if you have diabetes over the years, it will slowly damage nerve endings. It will slowly damage blood vessels. Okay? You can go blind by having diabetes that is not regulated. I happen to know a woman that goes to my local church that for quite a few years, she did not believe her doctor when her doctor told her she was diabetic. She absolutely did not believe it. She refused to receive any medical treatment for it. And I can tell you now today, for the past 5 years, she is blind. She's blind because she did not believe she had this disease. She would not accept treatment from her medical doctor, and now she's blind. Okay? This is very, very serious stuff. One final question for you before we kind of wrap up here. If you know, diabetes is a hard disease to therapeutically manage. Anybody that has diabetes knows this. Okay, so let me give you a scenario. If you live with someone that's diabetic and they pass out on the floor, and you call 911 and the paramedic team shows up and you say, my husband is diabetic and he has passed out, can the paramedic team assume that that man passed out because his blood sugar is too high? Okay, so I'm seeing some difference of opinions here. And I like that, right? That means we can discuss this, okay? Folks, diabetes means elevated blood sugar. But 9 times out of 10, people don't pass out because they have too high blood sugar. They pass out because they have too low blood sugar. So what the heck's going on here? Part of the problem with diabetes is that patients often use the wrong form of insulin, or they give themselves too much insulin, so they go from having an overly high blood sugar to an overly low blood sugar, and then they pass out. That's the problem, okay? Folks, I'm sure you have lots of stories. I got lots of stories. I know a gentleman that this happened to. He passed out. He was diabetic. His wife called the emergency line, 911. They got there. It turned out that this gentleman with type 2 diabetes, his doctor had prescribed 2 different forms of insulin to control his disease. The first form of insulin was a slow release insulin that he was to give himself once a day to control his sugar through 24 hours. The second form of insulin was a fast form of insulin that he is to use right before he eats a meal to control the blood sugar spike that happens after you eat food. Well, before going to bed, he is supposed to inject the slow release insulin, but he got confused and he injected the fast release insulin, and his blood sugar dropped horribly low. He went unconscious, and his wife could not wake him up the next morning. Fortunately, there's a good outcome to this story because the paramedics were able to figure out what happened. They were able to get his blood sugar up and he was okay. But this happens all the time with diabetic patients, that they take the wrong insulin or they take too much of the right insulin, their blood sugar drops, and bam, they fall unconscious. So, another question coming through the chat window. And please notice the wording. Is it more immediately dangerous to have too low blood sugar or too high blood sugar? I put the wrong words in. Is it more immediately dangerous to have too low blood sugar or too high blood sugar? Okay. All right, folks. So hopefully you can see from my story, it is more immediately, like right now, there's danger right now. It is more immediately dangerous to have low blood sugar because you can pass out and die from that. Having too high blood sugar is not immediately dangerous. If you have blood sugar that's too high right now, it's not going to kill you now. It's not going to kill you tomorrow. It's not going to kill you next week. But if you have elevated blood sugar for many years, it will slowly, because of inflammation that takes place, it will slowly damage your nerve endings so that you may lose eyesight. You might lose feeling in your fingers and your toes and your feet. It will damage blood vessels, so your circulation's not correct, so tissue gets necrotic because of that kind of thing. Okay, so high blood sugar is a slow wasting away. It is a slow damage to the tissue that ultimately will have a devastating impact. But low blood sugar is dangerous right now. If you have low blood sugar right now, you might pass away and die from that. Okay. Folks, do you have any questions about anything we've talked about today, or anything that you fear might be on Thursday's exam? Okay, I'm not seeing anything or hearing anything. So folks, you know, if you have questions, you can email me, but please don't email me. Please do not email me Thursday morning at 5 a.m. because I'm not going to get that, okay? But if you have questions, send me an email. Otherwise, study really hard, stay focused. Your test is on Thursday, opens at 7 a.m. Class lecture on Thursday will start at 12:55, and we will have our last lab activity before your second lab exam the following week, right? Things are really finishing up here. So if there's no questions, thanks for your time, folks. Study hard. Good luck on Thursday, and I'll see you for lecture on Thursday at 12:55. Bye for now.